Alright, so now we're going to be looking at reaction rates. So the first thing that we need to talk about is what's called the collision theory. And the collision theory is the theory that we use to explain how rates of reactions occur. So the collision theory says that if we're going to have a reaction, that we have to have collisions. So it's all about molecules colliding with each other, because when one molecule is going to collide with another molecule, those bonds are going to break. And if the bonds break, then new bonds can form, which will form your products. So the collision theory has about 3 parts to it. And the first part says that there must be sufficient number of collisions. Now, the more collisions that happen, the odds are better that the reaction will take place. Okay, the second part says when those molecules collide, they have to have enough energy so they don't simply bounce off each other, but they hit each other and then break apart the bonds. So not only do we have to have enough collisions, but we have to have collisions with enough energy that's going to break those bonds. Okay, and lastly, the collisions must have proper orientation. Meaning if I want a new bond to form between N and O, then I should have the N part of one molecule and the O part of another molecule colliding, because they're going to break the old bonds and the new ones are going to form. So if they're not colliding at the correct orientation, I'm not going to be making the new bonds that I need. We're going to look at a reaction progress diagram because you're going to see a lot of these. So we have the progress of the reaction on the bottom, meaning it's going to be going that way. And on this side we have the energy. And energy is usually in joules or kilojoules. So our reactants start out with so much energy. And those reactants then, hopefully, we're going to have enough energy in our collisions that we're going to break apart those bonds and start to form new ones. And at the top here, this is called the activated complex. And the activated complex occurs when I have the energy that's required to break the bonds is the same as the energy that is released when I form the new bonds. So at that point, when those are equal, I form the activated complex, and that's at the top of that hill. Now the amount of energy between the reactants and this activated complex is called the activation energy. And that's the energy that has to be overcome for that reaction to occur. So the energy from the beginning here at the reactants to that activated complex, that's your activation energy. And we could read on the graph, if we had numbers here, how big that amount of energy was. All right, and then once we overcome this hill, the reaction proceeds, and over here I form products. Now in this particular graph that I have drawn, there's a difference in energy between the reactants and the products. The reactants had more energy to start with than the products. The products have less energy. That means some of that energy was released. So this picture shows an exothermic or an exergonic reaction. If I wanted to see what an endothermic reaction looked like, so here's my reactants, my products, my activated complex, and this is my activation energy. I'm going to call this E for energy of activation. So in this case, my products have more energy than the reactants, which means I absorbed energy. So this is going to be an endothermic or an endergonic reaction. Okay, so we can learn a couple things. We can tell if it's an exothermic or an endothermic from where the reactants and the products are. We can also tell how large that activation energy is. And the larger the activation energy, the slower the reaction. Think about riding your bike up a hill. If that hill is really, really tall, it's going to take you a long time to get over that hill. So that means it's going to take longer time, which means the slower the reaction. If you have a very small hill, then you're going to be able to ride your bike up that hill really quickly, so the reaction is going to be quicker. So I can tell by the size of that hill between the reactants and the activated complex how quickly that reaction takes place. Because remember, that's the amount of energy that has to be overcome for that reaction to occur. Alright, so when we talk about reaction rates, there are things that we can do to speed up a reaction. And we're going to be talking about each one of these in terms of that collision theory. Okay, so the first thing that I could do to make my reaction occur faster is the temperature. The higher the temperature, the faster the reaction occurs. The lower the temperature, the slower it occurs. Now I need to think about that in terms of the collision theory. Alright, so if I increase the temperature, I know the particles are going to move faster and they're going to have more kinetic energy, which means I'm going to have more collisions occurring because I'm going to have these particles moving quicker, and we said they have more kinetic energy, so I'm going to have more energetic collisions. And as long as I have those things happening, more collisions, more energetic collisions, that should help my reaction go faster. Okay, the second thing that I can do is change my concentration. Okay, so the concentration means I'm adding more stuff to it. The higher the concentration, meaning the more stuff that I have in there, the faster the reaction. If my concentration is lower, then it's going to be slower. So let's again go back to the collision theory and see what that means. Alright, so if I have more particles packed into my container, they're going to hit each other more often. So I'm going to have more collisions occurring. And if I have more collisions occurring, the reaction should go faster. And if I have more collisions, odds are that enough of those are going to have the right amount of energy, and hopefully enough of those have the proper orientation. So by overkilling on our number of collisions, we can hopefully reach these other two criteria. So just overload on the collisions. Hopefully some of those have more energy and some of them have the right orientation. So because we have more particles, we're going to have more collisions. Okay, and the third one is the addition of a catalyst. Okay, and a catalyst is something that speeds up the reaction by lowering the activation energy and it is not a reactant or a product. It doesn't show up in my equation. Sometimes it may occur, like you may see it written in like over the yield sign, but it's not going to be listed as a reactant or a product, and it is not used up in the equation or not in the reaction. It's not consumed, meaning it's still there at the end that I could use it again. Examples of catalysts, these would be things like enzymes in your body would help the reactions go faster. Now in terms of our diagram, what this does to our reaction progress diagram is we said that the activation energy is that hill. So let's say that this was my normal reaction. If I were to add a catalyst, it's going to make this activation energy much smaller. So when I add a catalyst, that lowers that hill. And remember, we're thinking about riding a bike. If the hill's smaller, you're going to be able to get over that hill faster and the reaction will occur quicker. Alright, so that should take care of reaction rates.